these issues.
Introduce myself to whom doesn't know me. Fortunately, I don't have a fantastic connection, so I will hide myself during the talk. Thank you very much. Thank you to Giovanni for this very interesting talk. Okay, so I will move to experimental consequences of the arguments which were so nicely introduced already, and Andrea will deepen on the theory. So we are performing several kinds of measurements, all involving tests of PP for electrons specifically. And they are performed at the Gran Sasso under Mountain Laboratory. This is a very particularly suitable environment for testing, for performing high sensitivity measurements of extremely low rate physical processes. This is due to the fact that the shielding of the mountain traduces in a reduction of the cosmic flux of 6 orders of magnitude, more or less. And essentially what we have to face there is gamma background coming from primordial isotopes, not only from the mountain, the concrete you can imagine, which stabilizes the lab, but also even if we try to reduce to the minimum in our experimental setup, still some residual radionuclides survive. I will just mention a class of experiments. I will not go in the details of this because it's not the argument of my talk today, but so I showed here, we are here and there. This is not a kind of ubiquity of our experiments. It's simply that we are performing many in parallel. One class is devoted to those kind of modification of quantum field theories which respect the so-called Messier-Greenberg super selection rule. Is a theorem of quantum mechanics stating that the transition probability between two different symmetry states is not permitted, which means that to test this kind of models you have to use open systems. With this I mean, since we test the in-statistic theorem for electrons, what we do indeed is to introduce new electrons in a pre-existing system of electrons through a current, and what we check is the symmetry state which we prepared. To do this, we circulate a current in a copper target, and these kind of experiments are going on since the beginning of this century. We are now in the phase 2 of the experiment, and we are already preparing the phase 3, which is reviewed for the next year. But what I will speak today is another class of experiments still performed at Gran Sasso, which indeed are the first dedicated experimental tests to put the experimental constraints on the energy scale of emergence of non-commutativity, again through the test of PP for electrons. I'm sorry, I got a terrible flu. I really hope that you can hear me properly. So since all the predictions of deformation or violation of spin statistics in the context of non-commutative quantum gravity models slightly violate the super selection rule, we don't need any current, so the experiments are completely different. Indeed, the pool of test electrons which we use are simply the electrons which reside in the conduction band of huge, extremely pure conductors. In the experiment I described today, the conductor in particular is extremely radio pure Roma lead target, is these gray cylinders which surround the detector. So here the aim of the measurement is as the cleanest possible detector, and we use indeed the purest one. Is a coaxial p-type germanium detector, is about 2 kilograms of this germanium crystal. This is cached here, only the internal part of the setup obviously is much more complicated, a lot of layers of shielding and what on, and okay, you can find here some details I really don't want to enter. Just I wanted to communicate that we have a very good knowledge of our setup because we completely characterize the detector by means of a Monte Carlo dedicated, which allows, for example, to determine the background or to determine the efficiency for the emission of single photons in whatever part of the detector. No? Here, bottom left, for example, you can see the efficiency functions calculated for each part of the experimental setup. And here the efficiency is corresponding to the energies we are interested in. I will go in details very, very soon. So the results which I show correspond to total acquisition of about 2 months. And the goal of the measurement in this case was to look for a signature of PP violating K alpha and K beta transition from this LED target. When violating means that we assume the 1s level, we search for when the 1s level would be already occupied by 2 electrons. Now is immediate. You can imagine that if this happens, then the transitions from the higher levels will be shifted because the levels are less bound, and you can calculate with a high accuracy these shifts with an accuracy of few electron volts. I listed in this table the allowed and the forbidden transition energies for the transitions which we are looking for. And our aim is to extract the probability density function for the expected signal once you somehow subtracted the background from this measurement. So in blue, in this plot, you can see the data which we collected in these 2 months. You see the purity of the spectrum. The energy range was optimized by performing a lot of measurements of all the materials constituted the detector, from which we expect the activity, and everything we measured tells us that we just expect the transitions from the K complex in lead. Even if, as you can see, the K lines, the allowed one, are around 75, 73 keV, and so on, you see nothing about this flat background. So the detector is so radio pure that still even not the standard transition lines survive. Okay, so the detector, the target indeed is acting in this measurement as an active. So at the end, as you will see, what we do is to compare the upper limit for the signal which is given by this measurement with the signal which is expected by the theory according to different parameterizations that are available in the literature. And since this expected signal depends on the scale of non-commutativity emergence, you can put a limit, a lower limit on this scale. Now, as I will show in a second, the PP violation probability as envisaged by non-commutative quantum gravity models depends not only on lambda, but also on the energy. And for this reason, we wanted to perform a scan to check the sensitivity of the measurement. We repeated independently 3 separate analyses, looking for deviations from the standard transition, just the K alpha, then just K beta, and then the whole K complex. This is done for each parameterization which is tested. Now, from recent work from Andazzi and Antonino and others, you see that for a generic non-commutative quantum gravity inspired model, you can parameterize the deformation of the commutation-anti-commutation relation by means of this parameter, which resembles somehow the non-energy dependent Q parameter of the QO model from Greenberg, which is a purely algebraic model. This instead depends on the energy, namely this is the energy difference from the 2 levels of the transition and the study, and is related to the PP violation probability, this delta square, by a very simple relation. So you can take a power kind expansion parameterization, and according to the generic MK parameterization, you will have that at the first order delta square is proportional to E over lambda to the key. Now, key equal 1 would correspond to theta Poincare carré, but as you also heard, the case of theta Poincare carré is quite controversial. First of all, because the presence of spin statistic violation depends on the quantization procedure that you adopt. You have in Arzano-Marchesneau, but for example, in the FTN quantization scheme, you do not. Also, I would like to mention that the issue of the symmetry under the exchange of momenta of identical particles was already studied in the context of the Kappa-Minkowski non-commutative space-time by Amelino, Camellia, and Arzano. And there it was shown that indeed the overall structure of the interaction vertex is symmetric under the exchange of momenta. So let me say that mainly I will be concerned of the case of key equal to, which corresponds to theta Poincaré. And also very recently for theta Poincaré, there was a specific calculation of the atomic level p violating transition probability. This is found to get the first order correction in the phase, in the GM phase phi, and phi is exactly the delta squared p violation probability, and this depends on the choice of the value of the electric-like component. So if you assume it is vanishing, that you have that phi is somehow proportional to the product of the energy levels over lambda squared, while if it's different from zero, it is it's stronger. It's proportional to the transition energy difference among the two levels of the transition you look for and to the nuclear energy. So you have a much bigger gap in energy. So as I anticipated, the goal of the analysis is to extract the PDF of the expected signal. And in order to do this, accounting for all the uncertainties, experimental, we weight and the likelihood over the joint PDF of the vector of the experimental parameters. Obviously, we perform some choices of the priors, taking into account for all the previous experimental information on the subject. And the likelihood, as you can see, is parameterized like bottom left. So you have that the Ni is the number of counts that you observe. They oscillate according to Poissonians around the mean values. And the mean values, this is the crucial point of the analysis, is parameterized as bottom right. So you have a background component, B, capital B, and capital S are the total expected background and total expected signal. And the F determine the shape. So FB and FS are the expected shape of the background, which is given by the experiment, you can see in a second, and of the signal, which is given by the theory, obviously weighted on the experimental efficiency and acceptance. So as for what concerns the background, this is very simple. In this case, our spectrum, as I showed you, is flat in the background. So even by performing the best maximum log likelihood fit, you obtain this magenta distribution. Obviously, we excluded 3 sigma regions around each violating energy, where you would expect some signal from the theory. For the signal shape, the reasoning is a bit more involved. I just want to give you an idea. First of all, you start, imagine that you want to calculate what's the probability to observe K alpha 1 transition. Then you calculate what's the probability for an electron from the 2p to jump on the 1s, but conditioned to the fact that no other electron did it. Because otherwise, if there would be another electron already residing in the ground state, then again, the line which you look for would be shifted, and this would alter the expected shape. Then obviously, okay, you have to wait for the relative intensities of the transition from different J quantum numbers. At the end, you get that this correction is of second order, is not so important, and the rate is given immediately by the theory. So as I told you at the beginning, you expect the transition amplitude should be damped by a factor delta squared. So you recognize this tau factor, which is nothing but the lifetime of the PEP allowed transition from the 3P to 1S. And you have the efficiency factor calculated at the energy specific of the transition. Let me point also that obviously from the model you get that the deformation of the algebra would preserve at the first order the standard atomic transition probabilities. So obviously what we look for are transitions till transition from the 4p to the 1s is meaningless to look for higher order transitions because even the standard transition probabilities are negligible with respect to the K complex. So, okay, putting all together, clearly the probability to observe n violating transition K alpha 1 in the acquisition time is Poissonian. So finally, you get what's the expected number of events, of signal events from the theory mediated by the experimental resolution, and summing over all the K lines which you analyzed, analysis by analysis, you get the total number of expected events. Now, this is at the first order indeed. Besides this, you should consider other processes. For example, beside the one step, you have the possibility of two or more step violating transitions. Namely, what happens when an electron from a generic I shell undergoes a PP violating transition to one of the P levels, 2, 3, or 4, and then jumps to the 1s. But as you can imagine, the probability of such processes comes with the product of the delta square for the transition. So again, is a second order correction. And also analogously, subsequent violations from the same level are also second order corrections. So essentially, you get that the rate of the expected transition is the sum over all the K complex of these kind of rates here, which I showed you. So finally, you got the shape of the expected signal, because this is simply given by the sum of Gaussians. Is Gaussian corresponds to one violating P transition, so is centered at the energy corresponding, which I showed you, and the width is just the experimental enlargement, obviously, which is dominant, calculated at the corresponding energy. The intensities of the various transitions has to be weighted for the rates, which I showed you. Now, it's interesting that obviously the shape depends on the specific parameterization. It enters in the rate through the delta square, but obviously Fs does not depend on the scale, because this dependence is reabsorbed in the normalization. So here in green, for example, I show you what's the shape. This dinosaur is the shape in the case you look for violating transition from all the K complex, and in the specific case of the M3 parameterization. Okay, so you are done. At this point, you just have to calculate an upper limit for the expected signal from your data. And this you do, you repeat for each independent analysis and for each parameterization. Here, for example, I show you what's the joint posterior in the BS plane, background signal plane. In the case of the A1 analysis, so you look for deviation just from K alpha for the M1 parameterization. And finish. You can get an upper limit on the expected signal just by solving this integral equation. The probability level we choose is 0.9, and all these integrations were solved by means of a dedicated Markov chain algorithm, which has an uncertainty, global relative uncertainty of about 10 to the minus 5. And obviously, by comparing the experimental upper limit with the expected number of transitions given by the theory, you extract a lower limit on the non-commutativity scale. So in this table, I summarize which are the upper limits on the expected signal and the corresponding limits in unit of Planck scale for lambda for different analyses. So again, when you consider just K alpha, and then K alpha plus K beta and just K beta, and for the different parameterizations, luckily the fluctuations of the results are very small. And this is what you would expect if the analysis is consistent. The most sensitive analysis, again, you could expect is when you consider the whole K complex. So this as you can see in the case of generic parameterized power series expansion, you get an upper limit for the case of theta Poincaré of about 0.2 Planck scales. If you go more specific in the calculation, which I showed you before, and you compare with amplitude, which were calculated by Andrea and Antonino, you get respectively, in the case of electric-like vanishing component, a lower limit of about 0.1 Planck scales, while in the stronger case of the non-vanishing, you get a stronger limit, already about 300 Planck scales. So with this, I concluded. Thank you. I hope I was in time.
Thank you very much. Thanks a lot. So I would say, I know that Kristian has to leave soon, but probably we have time for one question if there's any.
No, obviously I will answer to whatever curiosity I'm here.
So is there any question for Kristian before he leaves, because he has to go for another meeting?